starting the recorder. So as I said, what we're going to talk about today is kind of a wrap up, a summary of the material that we've covered so far to deal with derivatives. You might recall from previous experience that wrap ups usually happen right before exams. Okay, and that is pretty much what's happening now. So I'm going to begin by sharing my browser with you, and we can take a look at that. Okay, let me just get that up. Okay, so here's our course, and we're currently in week 7. Okay, we did optimization with extrema last time. Today's topic is curve sketching, which, like I said, I mean, it sounds kind of old school, like why would you want to sketch a curve when you've got graphing calculators? That's true. But what curve sketching implies is you know enough from the function, its derivative and its second derivative, that you could draw the curve, without having a calculator. Okay, so it's a way to tie together the concepts behind derivatives. Okay, so think of it that way rather than as a pointless exercise in drawing something that you could get some other way. Think of it at the conceptual level. Like if I understood what the derivative's telling me, what the second derivative's telling me, I could conceivably graph the function by hand that it's coming from. Okay, so think of it as a conceptual test. I'm going to be using curve sketching notes today for class. And as I showed you our assignments, and I know some of you have started both of these, 2.7 and 2.8, as well as a discussion board. It kind of gets more at the concepts behind the math rather than math itself. Okay, here's week 8, which is coming up next week. And again, you can see there's no new material in week 8. Okay, we're going to be taking both sessions to go over the practice exam for exam 2. And exam 2 will be due kind of right before you start spring break. Okay, so spring break is the week after week 8. Okay, and hopefully you'll get all of this wrapped up in time to enjoy your week of spring break. Okay, so let me stop and ask anybody schedule questions. Okay, scheduling questions or what's coming up or what are we doing? Okay, as you can see, exam 2, it's a more based exam. Okay, I hate exams that are automatically graded. Okay, so you have the opportunity to upload your work for the exam after the fact. So when you're doing it, you're writing down your work as much as you can. And then once you finish with this one, upload the work here. That way, I'm going to go through all the exams just like I did with exam 1, look at your work, award you partial credit. Okay, that's kind of the best we can do in this situation that we're in. Okay, so think of it more like doing an exam on paper and then, the instructor grades it and gives you partial credit. So that's what I'm trying to emulate here. So again, anybody questions before we move on to the material in week 7? Okay, I'm not seeing any. And again, I'd encourage you, as always, don't feel you've got to write your questions in the chat. It's perfectly okay to unmute yourself, okay, and ask your questions. I actually welcome the conversation, okay? So don't hesitate to do that. All right, so what I'm going to be doing is I'm going to be opening these curve sketching notes to share with you. Give me a moment to do that. That takes me some time. Okay, and let me share those with you. Okay, now everybody should be able to see curve sketching notes. And again, I'll try to keep the chat open as long as it's not, blocking what I'm trying to display on the screen. Okay, so again, these notes are adapted but not completely copied, okay, from your text. Okay, so I kind of put my own words in here and I select things that I think are important to talk about. So that doesn't mean you shouldn't read the section of the text that's included, because again, it covers a lot more examples than I'm covering here. Okay, so like I said, what this is going to do, it's going to basically pull together all the information we can get from the function's derivatives. So get about function f from f prime and f double prime. Okay, so that's kind of the point of this curve sketching. Okay. So again, I'm not going to read things to you. I'm going to hit the highlights as we go along. Okay. So the first thing that we can tell from a derivative, a first derivative, right? We have to tell whether the function's increasing or decreasing. Okay. We can tell that because the first derivative is going to give us the slope of a tangent line. Okay, and so if the tangent line's got a positive slope, function's increasing. Tangent line has a negative slope, function's decreasing. Okay, and we could see that without ever having to graph the function, because again, we could find its derivative and evaluate it at a point and determine positive or negative slope. Okay, so here's a recap of what increasing means. Okay, what that means is, what this says, okay, in mathese is, as x gets bigger, okay, y gets bigger. Okay, so the x's are your x variable, and f of x is like y. Okay, so this says x and y are marching in the same direction. Okay, as x goes up, so does y. Decreasing says, as x goes up, y goes down. Okay, so they're marching in opposite directions. Okay, and I think everybody has a pretty good intuitive sense of what increasing and decreasing means. The trick to increasing, decreasing is always read your x values from left to right on the number line. Okay, always look at them from left to right. Don't go backwards. Okay. Right, so basically, here's kind of an intuitive graphical idea. If the function f is increasing, as you move from left to right, the height of the graph is increasing. In other words, x and y move in the same direction. So here we've got increasing and decreasing, right? So now this is a little bit trickier because it asks you to play with interval notation. And again, some of you have probably seen it and worked with it extensively, and some of you not so much. Okay, so this is an opportunity to kind of work with that. Interval notation is widely used in higher math, and I know some of you are thinking right now that I'm not going to take that kind of math. Never say never. Okay, you don't know where you find yourself in 5 or 10 years, okay, and what you'll need to do in order to advance in your career. Okay, so let's talk about intervals. Again, remember, intervals in this example will be just x values.
I'm sorry, I'm not able to see your oh, okay, I can see your screen now. For some reason, it was so large, I couldn't see what you're doing.
Would it be better if I made it smaller?
Oh, no, no, it's fine now.
Okay.
Yeah, it's
Yeah,
fine now.
just shout out, Cornell, if anything ever goes wrong. And guys, this is true for everybody. If something's not working, let me know. Okay, because again, I'm only seeing what I'm seeing. So thank you for bringing that up.
Thank you.
All right, so intervals in this case are just going to be the x values. Okay, and again, I'm bringing that up because some intervals, particularly the ones where you don't include endpoints, look exactly like ordered pairs. It's an unfortunate overloading of the notation in math, right? You see parentheses with two numbers separated by a comma. You're kind of conditioned to think of that as an ordered pair. But in this instance, you might want to consider it as an interval where both of those values are x values. How do you know which one it is? Okay, context. Just like how do you know what a word means? Okay, it's kind of how it's used in the sentence. All right, so here we're talking about intervals. okay? And the word interval is actually in the sentence. So we know that if I see something that looks like parentheses with numbers in it, both of those are X values, okay? I noticed on some of the exams, the previous exam, a lot of you got confused with that and you're putting Y values in your intervals when that wasn't appropriate, okay? So again, pay attention. If you're talking about a maximum or a minimum value, then you're probably going to have an ordered pair with an X and a Y. Because remember, the Y value is the maximum or the minimum, okay? So again, that's one of the confusing usage things with mathematics. It is a separate language, okay? So every time I have the opportunity to point those things out to you, I will. And again, I'd encourage you to ask when it's not clear. So we're going to have just intervals, okay, where the function's increasing, decreasing. One way to do this is to kind of find where it's changing, where it's turning around. So I see a turnaround point here, okay, and I'm going to draw that down to the x-axis. I see another turnaround point here, okay. I'm seeing kind of a turnaround point here. And then there's this flat spot in the middle, okay? And I'm just going to kind of draw down to the x-axis with the corners of the flat spot, okay? So why did I do that? Because the turnaround points separate, okay, the parts of the function that are increasing from decreasing, right? You can see here, this turnaround point, the function increases up to it, decreases away from it. It's decreasing down to this turnaround point and increasing up away from it. Okay, one other way to think about it, these turnaround points are where your derivative is going to be zero. Okay, your slope of a tangent line. Okay, you'll have horizontal tangents at those 3 points. Okay, and that means that the slope of the tangent line has to change from positive to negative or negative to positive. Otherwise, it wouldn't be zero at some point in the middle, okay? And again, if it's helpful to you, you can even draw little tangent lines so you can see what's happening, okay? But you do have to remember, okay, what a positively sloped line looks like, what a negatively sloped line looks like, okay? So if I look at this graph, I can see the function's increasing from 0. And again, let me put a 0 here. There's no mark over here, so I'll say that's about 0.5. Okay? Everything else that's significant looks like it's marked. Okay? So the function looks like it's increasing from 0 to 0.5. Okay? And again, I'm not including the endpoints because right at 0.5, the function's turning around. Okay. And again, I'm not sure what's exactly happening at 0, so I'll exclude that bit. Okay. Nobody would complain if you used a square bracket over here, provided they made it clear there was a dot over here at 0. Okay. So don't worry about that so much. Just in general, when you're giving intervals that aren't obviously closed with dots on them, okay, leave them as open intervals where you don't include the endpoints. Okay. All right. What other areas is it increasing on? Well, it looks like it increases from 2 to 3. Okay, because you can see again, I have a positive slope to my tangent line there. Okay. And it also looks like it's increasing from 4 to 6. Okay, because I have a positive slope there. Again, I'm going to stick to red for the positive slopes and the negative slopes. Okay, so there you can see again, 4 to 6, the function's increasing. Okay, now again, pay attention to directions on the exam just to keep your frustration levels down. If they tell you to separate the intervals with commas, do that. Okay, or you can use the or symbol, right? This is a union symbol, it's red or. Okay, again, pay attention to the directions, okay, on how you're doing it. If they just say list the intervals, typically you use the set notation in between them. Okay, and you can find that in, when you actually click in the box and more, it gives you the option to bring up a template, and that symbol should be in there. Okay, again, this is why I'm asking you, practice with the homework and then ask me those kind of questions if you get stuck. Okay, so again, depends on how it's worded. More often than not, more will like it like this. Okay, although there's nothing wrong with putting in the commas. Okay, so let's take a look at decreasing intervals. Okay, I've got the first one here. It looks like it decreases from 0.5 to 2. And then it looks like another decreasing interval would be from 6 down to 8. Because again, I could draw my negative sloped tangent line there. Okay, and then again, if you want, you can put the or, the union symbol in there, saying either in the left interval or the right interval. The other trick that I know some folks have trouble with intervals is just like the number line, okay, just like I went from left to right when I did this, the left-hand number in the interval is the low one, okay, so low on the left and high on the right. Okay, and they're all ordered that way, just like an X number line. The left numbers are smaller, the right-hand numbers are bigger. Okay, I know some of you tend to put your stuff in backwards. Okay, so again, those are conventions for using interval notations. Okay, so now you're probably thinking, hey, she left out a bit. She left out the bit between 3 and 4. If I look at 3 and 4, the function is constant on that interval. Okay, because it looks to me like this is a horizontal line, and that means the y value isn't changing. Okay, so I should have covered all of the x values between 0 and 8. They should be in one or another of these intervals. Okay, so is everybody okay with this exercise? Okay with example 1? Everybody all right with it? Okay. Thank you for the feedback. I appreciate it. Good. Okay, so what does the derivative tell us about increasing, decreasing? Okay, so if a function is increasing, okay, then its derivative will be positive for all x in that interval, right? So again, in these intervals, this function will have a positive derivative. Okay, if it's decreasing, then in those intervals, that function will have a negative derivative. Okay, if the function is constant, namely, it has a horizontal tangent line, let's just draw it in. Okay. Okay, then basically we've got a 0 derivative there, and it says that. Okay, so again, horizontal tangent line, 0 derivative. Okay. And again, that's no news. We've kind of done that before. So let's take a look at another example. And again, I'll try to get this out of the way. So I have a function over here, and it's showing the height of a helicopter during a period of time. Okay, so take a look. We've got time in minutes at the bottom. Okay, so my input variable would probably be t. And then here's the height of the helicopter in feet above the ground. This would probably be h of t. Okay. Now again, they want us to sketch the graph of the upward velocity of the helicopter, dh dt. Okay, another way of putting that is they want h prime, and again, I'm having a problem with my notes. So just give me a second. I'm having a little bit of trouble with my I'm not able to get my pencil to work. Hold on. Let me see if I can hear it. This happens from time to time. I apologize. While I'm trying to get my tech to work, let's just take a look at this graph. Again, you can see velocity is the derivative, the first derivative of position, okay? So the helicopter starts here on the ground. It goes up, it hovers for a while, it comes back down, hovers for a while, goes back up, and comes back down and lands, okay? So again, what we're looking for here is the graph of the derivative of this function. Now this function, if you take a look at it, tends to look like a fourth degree function, okay? And so our derivative is going to look like a third degree function, okay? We're going to start out by graphing the turnaround points. And again, I haven't managed to get my tech to work. So again, you're going to have to please excuse me for a minute while I try to get this to work. Trying a bunch of things. Sorry. Apologize. There we go. Okay, that was interesting. All right, so basically, if I want to graph the derivative, I'm going to try to graph the same sort of axes on here. Okay, so I'm going to put my t-axis in the middle. Okay, so here's t, and this will be h prime of t, or dh dt. Okay, so it's the rate of change, okay, of position with respect to time. So I could call it velocity, or, right, first derivative, or dh dt. Now I'm not going to put numbers on here, okay? I'm just going to try to graph my function. Okay, what I am going to try to put on here are my x values. Okay, and I have enough for 7. My t values, I'm sorry, this is time in minutes. Okay, so in order to draw the derivative graph, the first thing I'm going to be interested in is where is the velocity 0. So in other words, we've got this thing, position is going up, it's hovering for a second, then position's going down, hovering for a second, going up, hovering for a second, okay? So right here at 2 minutes, okay, I know my velocity is 0. Okay, how do I know that? 2 reasons. Okay, this is the height of the helicopter. It's not going up or down right there. Okay, so its velocity is 0. Another way to think of it is from the mathematical point of view, this graph has a horizontal tangent here. So its derivative graph will have a 0 there. Okay, likewise, okay, at 3 minutes, we've got the same thing. The helicopter descended and it's hovering for an instant before it goes back up again. So right at 3 minutes, its velocity is also 0, okay? And this graph would have another horizontal tangent line, okay? Last horizontal tangent line is going to be up here at 5 minutes, where the helicopter rises and then stops for a minute before it comes down again, okay? And I don't mean a minute, I mean an instant, okay? before it comes back down again. But again, you can see horizontal tangent at 5 minutes. Okay, so these are the zeros of my derivative function. Okay, this is where the tangent line to h of t is horizontal, so its slope is 0. Okay, so plot those first. Then what you look at are increasing, decreasing. Okay, in this first interval before we get to 2, my position is increasing. Okay, basically the function has a positive tangent line slope. Okay, that means my derivative has to have a positive y value. Okay, so between 0 and 2, my derivative's y value's got to be up here in positive territory. Okay, so basically I'm going to draw my line from the top down like this. Okay, and again, I'm trying not to draw straight lines because again, this is a curve. Okay. Then you can see from 2 to 3, this original function is decreasing. Okay, because it has negative slope tangent lines. That means from 2 to 3, okay, basically what happens is the derivative y values are going to be down below the t-axis in negative territory. Okay, so that means also that there's got to be a turnaround point in here somewhere, an inflection point, okay, where the thing turns around. I'm going to put that right in the middle between 2 and 3. Okay, where it goes from being concave down to concave up. Okay, and that means this function will turn around. Okay, and again, you can see I'm hitting a 0 at 3. Okay, if you look from 3 to 5, you can see the function is increasing, which means from 3 to 5, I've got a positive y value on my derivative. And somewhere in here, it's going to turn around from being concave up to concave down. Let's put that at 4, okay, just because I'm eyeballing my graph. Okay, but positive y values on the derivative mean that you have an increasing function. Okay, here's my last 0 at 5, and you can see the function decreases all the way out to 8. Okay, so that means this is going to be negative all the way out to 8. Okay, however I decide to draw it. Okay. So does everybody understand how I did that? I understand how I sketched that curve. Understand how I sketched that curve? Okay, anybody got questions about what I did? Okay, the important thing to connect is slope of tangent line here, positive or negative, affects y value or the vertical value of your derivative curve. Okay, so again, rather than making this look weird, I'm just going to have it look like this. Okay, and again, try not to look at it as a straight line. Okay, so if this is a 4th degree polynomial, okay, if we had actually had the equation of this function h, okay, we would have been able to differentiate it manually, okay, using the power rule, and we would have wound up with a 3rd degree polynomial, right? Because the power rule says subtract 1 from the exponent, right? And then drop the exponent by 1. Bring your exponent forward, then drop the exponent by 1. So whenever you differentiate polynomials, you'll notice you'll drop the degree by 1. Okay, and hopefully to everybody who took college algebra, even if it was a while ago, you can recognize this as a 3rd degree polynomial. Okay, so that's an additional sanity check. Okay, that it looks third degree, okay? Derivative, I guess I'll say h prime of t looks like a third degree poly. Okay, that's a sanity check. Okay, so if you're having trouble drawing, look at it and say, hey, this looks like fourth degree. This should look like third degree. That might help you draw it better. Okay, use all of the information you have. Okay, so again, everybody's good with this. So let's move on. Okay, so this is kind of part 2 of that last box. Another way to look at it is this is the converse of all those statements, namely you switch the if-then pieces. Okay, so the other one said if you've got an increasing function on an interval I, it's going to have a positive derivative. This says if the derivative's positive, then the function's increasing. Duh. Okay, not every statement in math has its converse being true, but these do. Okay, so essentially all these are saying is positive derivative in an interval means the function's increasing. Negative derivative means the function's decreasing. Zero derivative means the function is constant. Okay, so just like the other half of that last box. Okay. And again, it's important to state that so you know that it works in both directions. So here we have use information about the values of f prime to help graph this cubic function. Okay, so then they're going to walk you through the steps. Now remember, the point of these exercises isn't to create the graph. I can do that with Desmos in a minute. Okay, the point is to use the derivative to tell you what's happening with the function. Okay, it's to see what kind of information the derivative tells you. So they're going to walk me through steps. They tell me take the derivative. Okay, so let me do that first. And again, it's a polynomial. It's a cubic polynomial. So I'm just going to do power rule, power rule, power rule. Okay, bring down the exponent, drop the exponent by 1. Okay, pull away the constant, the coefficient, bring down the exponent, drop the exponent by 1. Okay, pull away the coefficient. Okay, the exponent here is a 1. Okay, drop the exponent by 1 gives me x to the 0, right? And notice all of these terms dropped by a degree. The cubic term became a square term, the square term became a linear term, and the linear term became a constant. Remember, plus 1 doesn't give us anything, okay? So I'm not going to write plus 0 here. And cleaning it up a bit gives me 3x squared minus 12x plus 9. Okay? Set it to 0 to find the critical point. So that's 0 equals 3x squared minus 12x plus 9. Okay, so looking at my polynomial, the first thing I notice is, hey, I can divide a 3 out of all of those terms, which is going to make this a lot easier to work with. Okay, so divide out a common factor. Remember, if I'm not taking out my variable with this 3, it's not going to yield any zeros, any solutions. Okay, so this is just a 3. I could throw it away. It's not going to affect where this function is 0. Okay. Then I'm going to see, well, is this a factorable polynomial? Well, my last term's plus, okay, and my first term's x squared. So what does that tell me? That tells me I've got an x as my first term in both these factors. The fact that this is a plus means the two signs in here must match, okay, because that's the only way you get a positive product, okay? So basically, these have to be the same. And since this sign is negative, it tells you they're both negative. I'm lucky there's only one way to get 3 as a product with whole numbers, and that's 1 and 3. Okay, so that's how it factors. Okay, set each factor with the variable in it equal to 0. And solve. Okay, so I'm going to add 1 to both sides here, add 3 to both sides here. Okay, so my critical numbers okay, are x equals 1 and 3. And if I'm interested in critical points, I have to figure out what the y values are that go with that, okay? That's a calculator problem, okay? I can just plug in my 1 here and solve for the f of x value, f prime of x value, right? I have to plug it into the original equation, okay, to see the y value that goes with it. I'm going to bring up my TI just to show you that. Let me share the TI with you. Okay, so everybody should see my calculator. And again, you're going to start with this one. You can put it in y equals and graph it. You can just evaluate it like this. You have 1 cubed minus 6 times 1 squared. Oops, I'm still up in the exponent. Okay, let me get rid of that. Forgot to step out of the exponent. Minus 6 times 1 squared. Plus 9 times 1 plus 1. Okay, so that value is 5. So one of my critical points is 1, 5. Okay, the other critical point would be the same original f of x with 3 plugged in. So I'm going to get the calculator to repeat what I typed in last, and then just go back and change the 1 to a 3. You can also do this on the Web 2.0 calculator, okay, because it has a memory. It retains the last thing you typed in. So you can just go back and retype over that if you don't have a scientific calculator. Okay, the next one I'll use the Web 2.0 calculator just to show you both ways. Okay, so these are my critical points. What does that mean? In the graph of f, these are the turnaround points. Okay, it's a 3rd degree polynomial. It should turn around twice. Okay. All right, what else do we know? Okay, here's one way you can do it. Determine the sign of the derivative in each interval created by the critical points. Okay, well, let's put our critical numbers here. I've got 1 and I've got 3. That divides the number line into 3 intervals. Okay, so I've got, if you think about it, this is my number line. I have negative infinity up to but not including 1. I have 1 to 3. And I have 3 to positive infinity. Those are my intervals. Okay. And then what you want to do is pick a test point. In each interval. Okay, this isn't an art form or anything. Okay, the only thing I can suggest to you is when you have an interval like negative infinity to 1, pick 0 in that interval. Okay, so let's choose 0 in the first interval. Okay, from 1 to 3, let's choose 2. Okay, and from 3 out to infinity, choose 4. Okay, so my strategy is to pick points that are easy to work with. Okay, so these are x equals points. Okay, then I'm going to use the factored form of my derivative. Okay, so I'm going to go back here, and I'm going to use this. Okay, so my derivative, f prime of x, was 3 times x minus 1, x minus 3. Okay, and I'll show you why this is so easy. All I care about is the sign of the derivative. Okay, so choose a test point, check the sign of f prime. right? Evaluated at that point. Okay, so I just want to know what the sign of it is. Okay, so I'm going to have f, oops, sorry. F prime of 0. That's 3 times 0 minus 1, 0 minus 3. So I'm just plugging in 0 in place of x here. Okay, then all you have to do is look at the signs of each factor. Plus, 3 is positive, 0 minus 1 is negative, 0 minus 3 is negative. Okay, so 1 positive and 2 negatives, right, gives you what? It makes it positive, right? So in other words, what I'm saying is positive times negative is a positive, right? So I'm looking for pairs of negative signs to make a positive, yeah? All right, then let's do this. Notice I didn't have to touch a calculator to do it. So now I'm going to plug in a 2. That's going to be 3 times 2 minus 1, 2 minus 3. So again, just plugging in for the x, positive. 2 minus 1, that's also positive. 2 minus 3, that's negative. All right, 2 positives and a negative multiplied together gives me a negative. And the last one, I'm going to plug in the 4. And that's 3, 4 minus 1, 4 minus 3. And I think you can tell here everything is positive, positive, positive. So this one's positive. Okay? So use this information to decide where the function is increasing, decreasing. I'm going to put this information on my little number line. Okay, and you can see it right here. And then it's real easy, okay, to just copy my intervals. I've got 2 intervals where the function's increasing from negative infinity to 1 and from 3 to positive infinity. Everybody see that? It's where the derivative had a positive sign. Okay, so increasing from negative infinity to 1 or three to infinity. Okay, and then decreasing. There's only one interval where my derivative had a negative sign, and that's from 1 to 3. Okay. And again, I would be able to at least graph the shape of this function. I wouldn't know what the y values are on the function. Okay, but here's sort of what it should look like. And this is the original f function, right? Basically, I have a critical number at 1 and a critical number at 3. And I know to the left of my critical number, okay, 1, my function's increasing, okay? So it's increasing up to that, right? So this is going to be a max, okay? And it's decreasing away from it, all right? Here's my other critical number, decreasing down to 3, and then increasing up and away from it. Okay, now again, I don't know exactly why did we choose. Okay, they are in the intervals separated by the critical numbers. Okay, so the first thing I did when I drew the number line is I put on the 1 and the 3 that I got from setting the derivative to 0. And then it is up to you to pick a number in each of these intervals to test. Okay, I picked 0 in this first interval because 0 is easy to do arithmetic with. I picked 2 purely because it's in the middle of this interval. And I picked the 4 here because it's a smaller number. I mean, 50 would have worked just as well, but 50 is kind of hard to do arithmetic with, okay? I picked the smallest numbers that work. Did that answer your question? So the only condition is basically pick numbers that work in these intervals, but the actual choice of number is totally up to you. Okay, I'm picking numbers that I think will be easy to use. Okay, that's a great question. So again, if you look at my graph, okay, these values, these y values may be somewhere else. Like this y value may be way up here. This y value may be below the x-axis. That's fine. What I'm showing you is this point. I think this was 1, 5. Okay, because again, remember, I found the critical value. That was a local maximum. Remember, I got the critical points over here. Okay, the other one is 3, 1. Okay, so because I did get the critical points, I do know where these are. Okay, and now I have an actual graph. I was able to graph f purely from the information given by the derivative. Okay, see how I used to graph f. So I use the derivative to create this graph. Okay, and again, the point isn't to create a graph by hand. The point is to understand what the derivative's telling you. If I just had the critical numbers 1, 5, and 3, 1, okay, you might say, well, I know 5 is bigger than 1, so that has to be a relative maximum. Yeah, in general, that would be the case. Okay, but the derivative gives you the extra proof that you're increasing up to this, decreasing away from it. Okay, decreasing down to this one and increasing away from it. Okay, everybody okay? Can you just give me a yes or no? Okay, so far. Just give me a yes or no. Good. Okay. Well, let's talk about the second derivative then. And what does that tell you? Okay, remember the second derivative talks about concavity. First derivative is increasing, decreasing. Second derivative is concavity. Okay, so again, if your function is concave up, your second derivative, 2 plus signs, is positive, right? The smile is a concave up curve. Up, right? And if your second derivative is negative, concave down. Okay, the frown is a concave down curve. Okay, so that's like a little mnemonic to help you remember what the second derivative tells you. Okay, and it's true for all the x values in the interval. Okay, and the converse is true. Namely, if you've got a positive second derivative, then your function's concave up on the interval. If you've got a negative second derivative, the function's concave down. So again, switching the if and then part of the first statement. Okay, so it works both ways. Okay, so let's see what we can figure out. All right, just so you know, what we did here is usually called the first derivative test for maxima and minima. In other words, we use the sign of the first derivative to tell us whether these critical points were maximums or minimums. So I know this is a max, and that's a min. Okay, so you can see there's a fair amount of work going on there. Okay, let's see if we can do a second derivative test that will help us find inflection points and will also tell us about maxes and mins. Okay, so this is the same function, just so you know, and we know f prime of x. I'll just copy it over. Okay, there's our first derivative. Okay, this is the same function we were working with before. So I'm going to differentiate it again. Okay, and I'm starting from the first derivative. Okay, so pull away the coefficient, bring down the exponent, drop the exponent by 1. Okay, x term, pull away the coefficient, bring down the exponent, drop the exponent by 1. This x term drops out again. And again, notice that I've done the same thing when I differentiated a second time. Each term dropped by a degree and I lost the constant. That should be a pattern you see now, okay? So my second derivative is 6x minus 12. Okay, we're going to set that to 0 to see if we can find some inflection points. Okay, because again, remember, second derivative 0 can give you inflection points. Okay, sometimes it gives you cusps. Okay, don't worry about that just yet. Okay, if I solve this for x, first I'm going to add 12 to both sides. And then I'm going to divide both sides by 6, which gives me 2 equals x. Okay, so there's an inflection point here. Okay. Everybody good with finding the inflection point? What that means is concavity changes. At x equals 2. Okay. So let's determine the sign of the second derivative in the intervals created by the inflection point. Okay, so here's my 2. That divides my x number line into 2 intervals. Again, remember you've got direction posts there. So your first interval is negative infinity to 2 and 2 to infinity, again, not including either endpoint. Okay, and you can do the same thing we did. We're going to pick a test point in each interval. Okay, and I'm going to check the sign of the second derivative. Check the sign of the second derivative. Okay, so I'm going to ask you guys, okay, pick a test point just so you're sure I'm not like gaming the system somehow. You pick a test point in the interval negative infinity to 2. Okay, just throw one out there in the chat or unmute yourself. Who wants to pick a test point in that interval?
0.
0, yeah, okay, 1, 0, wouldn't matter, okay? So me's picking 1, that's perfectly okay. I'll do it with both of them so you can see that it works, okay? And I didn't catch who said 0, so 0 is the other point. Okay, so x equals 1. Okay, so then we're just going to take the second derivative, plug in the 1. Okay, and that was 6 times 1 minus 12. Okay, 6 times 1 minus 12, that's 6 minus 12. That gives me a negative number. Okay, here was the other f double prime of 0. 6 times 0 minus 12. Okay, this first answer was negative 6. This second answer is negative 12. It doesn't matter, they're both negative. Okay, so I'm telling you, whatever point you pick in that first interval, you're going to get a negative value. Okay? How about a point in the other interval? I pick a point in 2, pick a point in 2 to positive infinity. Somebody else want to pick a point in this other interval? Okay, we've got 4 and we've got 3. Okay, let's try Fabian's 4. Okay, and then we'll try the 3. Okay, here's 4. So 6 times 4 minus 12. Okay, that's 6 fours are 24 minus 12, that's positive 12. And let's try the 3. F double prime of 3. 6 times 3 minus 12, that's 18 minus 12, that's 6. Doesn't matter, they're both positive. Again, I don't care about the number, I care about the sign. And whatever value you pick in this interval will give you a positive second derivative. So I'm going to put those symbols here, negative over here, positive over here. Okay? And what does that tell you about concavity? It says concave up on negative infinity to concave down on 2 to infinity. Okay? Now, again, let's see if we remember we had critical numbers for this function. One of them was 1 comma 5, and the other was 3 comma 1. Okay, so you have to look at the two critical numbers. Remember, these are x, y ordered pairs. And you have to decide what interval they're in. Okay, now the intervals are just x values. So I'm looking at the x value only. 1 is going to be in the first interval, negative infinity to 2. Okay, 3 is going to be in the second interval, 2 to infinity. Okay, so again, what this is saying is if the function is folks, I got it backwards. Nobody stop me. Okay, negative second derivative means concave down. Okay, concave down, negative second derivative, concave up, positive second derivative. Okay, so again, guys, if you see me make a mistake, please shout it out. Okay, so again, second derivative is negative, concave down, positive, concave up. Okay, so I had my up and down backwards. Okay, but these critical numbers are in these intervals. Okay, so we're saying my function is concave down in the first interval, concave up in the second interval. Well, if it's concave down, this must be a max. And if it's concave up, this must be a min. Right? Because my maximum would be sitting on top here and on the bottom here. Okay, so this is the second derivative test for maxima or minima. Okay, so either of those derivatives will tell you similar information. It's just a matter of, which one you'd prefer to do. My advice is if you've got polynomials, use the second derivative test. Why do I say that? Polynomials have no weirdness in them. Certain other types of functions, it might be easier to tell what's going on by just checking the sign of the first derivative on either side. Okay? Everybody understand example 4? Okay, with example 4? Yeah? Okay, so first derivative test, second derivative test. Okay. Let's take a look at a weird function. Okay, so I'm going to run through example 5. And I'm trying to keep an eye on the time. Okay, again, I'm not going to get to go through all of the examples in class in this section, but when I upload my notes, for sure, I'll have all the examples worked out. Okay, but I want to make sure to show you some of the graphical stuff, okay, as well as the stuff that involves cranking through taking derivatives. Okay, but let's look at this one. Okay, anybody know what kind of function this is? Anybody know what that's called? Function. okay? It's not exponential because x is not in your exponent, okay? You could think of it as a radical, okay? It's basically you're taking the cube root of x squared. Okay, so you could think of it as a root function. You can also think of it as a power function. Okay, because again, you've got a power here, but it's not a polynomial because this is not a whole number. Okay, so again, it's a cube root because that's in the denominator of your exponent, and x squared is in the numerator. Okay, and again, not an exponential because those have x up in the exponent. Okay, again, it's important because your strategies kind of change depending on what kind of function you've got. Okay, now because this function may give us undefined points in the derivative, notice the directions. Take the derivative, set it to 0, that's all the same. But I should also check for places where f prime is undefined. Okay, because again, I'm not using a nice polynomial function here, so I need to check. Okay, so let's take a look. F prime of x. It turns out I can do the derivative exactly the way I would with a polynomial. Use the power rule. That says bring down my exponent, drop the exponent by 1. So that's 2/3 minus 1. And again, you calculator if you're not sure about the fractions. This gives me 2/3 x to the minus 1/3. Okay? Another way to write this would be 2/3 x to the 1/3, or this could also be a cube root. Okay? There's no point in oversimplifying it because what 0. Like that. Okay. Now here's my question to you. What's my next algebra step? In solving for x. What's my next algebra step in solving for x? Feel free to unmute if it's too much to type. What would I do next? Yeah, multiply the denominator on both sides. You might remember when you've got algebraic fractions, you want to clear the denominators. So I'm going to multiply both sides by 3 times x to the 1/3. Okay, you can see these cancel out. And I get okay, everybody all right with that? Everybody comfortable with that? Okay, what's the value of the left-hand side of that equation? What's the left-hand side value? Right here. Right, I put a 0 there because it said set the derivative to 0. Now I'm multiplying both sides by 3x to the 1/3. That 0 is still there. So what's this value on the left side? 0. Yes. So here's what I've got. 0 equals 2. What do you think about that? What do you think about 0 equals 2? Trying to help you discover what to do with weirdness. Yeah, it's a false statement. Okay, false statement. No amount of help from X is ever going to make 0 equal 2. Okay, so a false statement tells you you made a wrong assumption when you started. Okay, you made a wrong assumption. Now, what was that wrong assumption? The wrong assumption was that you could solve the equation for X. Okay, that's what you tried to do. You set one side to 0 and said, oh, let me solve for X. That was the wrong assumption. There's no solution. Okay. So kind of like when you did systems of equations way back when in introductory algebra and a variable dropped out and you got a false statement like 0 equals 2, you said, oh, this system doesn't have any solutions. I've got 2 parallel lines or whatever. Same thing, okay? But what a false statement in mathematics means is there was some assumption you made that wasn't valid, okay? And that's what it was, namely, we can't find a solution. Okay. Well, that's not terribly helpful. Let's go back and look at our derivative, okay, which is this thing right here, f prime of x equals this. Is it undefined anywhere? Okay, so I'm asking you to look at f double prime equals 2 over 3x to the 1/3. Is it undefined anywhere? Yeah, when the denominator is 0, okay? And what x gives you a 0 denominator? What x value will give you a 0 denominator? This is just a cube root, folks. Okay. Yeah, 0. Okay. I can take a cube root of 0. You can take any root of 0. Okay. Square root, cube root. You have to remember here, x to the 1/3 is a cube root of x. Okay. So it looks a lot less scary. And if you don't believe me, fire up your calculator. Okay. I've got my TI up here. All right. And I'm going to raise 0 to the 1/3 power. And you'll see I get 0. Okay, that's the same as taking a cube root, okay, which I have to get from my math menu. See cube roots number 4. Put the 0 in there. Same thing. Okay, so again, get comfortable with these fractional exponents and what they're telling you to do. Okay, so you can see if I take the cube root of 0, I'm going to have 0 here times 3. That's still 0. So this is undefined when x equals 0. Believe it or not, this is a critical number. Okay? And if you put 0 into your original function, you can see your critical point will have an x value of 0. And what will the y value be? Well, I have to take 0 and raise it to the 2/3 power. So here's my calculator again. Raised to the 2/3 power. Well, what do you know? It's still 0. Yeah, what did I do? I squared 0, still 0. Took the cube root of it, cube root of 0 is still 0. Okay, so basically you can see my critical point is at the origin. Okay, so something weird happens with this function at the origin. All right, now I'm going to determine the sign of the derivative in each interval created by my critical points. Okay, I've only got 1, 0. So my 2 intervals are negative infinity to 0 almost, from 0 out to positive infinity. I've only got 2 intervals. And again, it's totally up to me what points, what the x values I want to pick as test points. So again, you might pick -1 in the first interval, and I might pick, again, -2. It doesn't matter. Okay, so again, we're going to try to pick things that are simple. So I'm going to evaluate my derivative at -1. Okay, and that's 2 over. Okay, and again, you might want to consider things if you're going to be doing it by hand, things where it's easy to take a cube root. Cube root of 1 is 1. Cube root of -1 is -1. Okay, and again, feel free to fire up the calculator, okay, and evaluate it. You can basically do it with alpha y equals numerator, denominator. Put your 2 up here, put your 3 down here, put in your -1, raise it to the 1/3 power, and boom, you've got a negative number. Again, I don't care what the value is, I just care it's negative. Okay, and again, I would do the same thing with the +1. And again, I promised I'd show you it with the Web 2.0 calculator. So again, I'm going to do the same type of evaluation. Just on the Web 2.0 calculator, I'm going to need parentheses around my whole denominator because it doesn't give me the fraction template. So let me just bring that up, close this one. Here's Web 2.0, and I want to evaluate 2 divided by parentheses 3 times 1 raised to the, now I have to pick a power here. Okay, the power also needs to be in parentheses, 1 divided by 3. Okay, and then close. And just check, this looks like what you expect. 2 over 3 times 1 to the 1/3. Again, +2/3, it's a positive number. That's all I care about. Okay, so again, you can use the Web 2.0 calculator. It's unfortunate it requires you to type it in with parentheses, but you've got this double check up here, okay, where you can take a look at that it looks like what you expect. If it doesn't, try parenthesizing your exponents and your numerators and denominators to get it to look that way. All right, so I know it's positive here. Okay, so I have a negative on this interval, positive on this interval. Okay, so I know the function's decreasing here, increasing here. Okay, and again, if I just want to say decreasing, -infinity to 0, increasing 0 to infinity. Okay, so I know the function's dropping as it comes towards the origin and then increases away from it. Next thing I want to do is check concavity. So I need my second derivative. Okay, so here's my first derivative. Let me just write this over again. The way it originally came out, okay, 2/3 x to the -1/3. Okay, again, remember, where did that come from? It's up here. Before I wrote it like this. I wrote it like this to try to see if it had an undefined spot in its denominator, which it does. Okay, but this is actually going to be easier to differentiate again because x has a power on it and it's not stuck in a denominator. Okay, so that's why I rewrote it like this. F double prime of x, pull away the coefficient, bring down the exponent, and then drop the exponent by 1. Okay? Then the rest of it is clean up. Okay, my coefficient is turning into something negative because I have my +2/3 times my -1/3. That's -2/9. And my exponent is getting even more negative. Okay, -1/3 minus another 3/3 is -4/3. Okay? And again, there's a possible inflection point here. Again, if I set this to 0, I'm going to have the same problem I had before. Let me rewrite it. Okay, there it is down in the denominator because it had a negative exponent. If I do the same thing I did before, you're going to get 0 equals -2, which is false. Okay, so no solution. Again, you can see you have an undefined spot in your second derivative at 0 as well. Okay, so it's a possible inflection point. Okay, I'm going to say possible inflection point at x equals 0, because why is that? Second derivative is undefined at 0. And it's undefined for the same reason. The first derivative was one undefined because this x here is in the denominator. Okay, and if x is 0, this whole expression is undefined. Okay, so possible inflection point there. I got to check. How do I check? I'm going to build a number line. I'm going to put 0 in here, and I'm going to test the second derivative at 2 test points. Okay, this is from -infinity to 0, 0 to infinity. And I'll use the same test points I used in the first derivative, only now I'm evaluating my second derivative, and I'm just caring about the sign. Okay, just caring about the sign. The other point was here in the other interval. And again, I can use my calculator to double check. All right, so let's turn it on. Alpha y equals, give me a fraction. Okay, my fraction actually has a negative sign out in front of it, so I'll put that there. Put the 2 upstairs, 9 downstairs. Then I have -1 raised to the 4/3 power. Okay, that looks like this one. Okay, and the sign on that is negative. Okay, I'm going to do it again, only I'm going to plug in a +1. So I'm just going to delete the negative sign. Oh, wow, look, I got a negative value. Okay, part of the reason you're getting a negative value is because, again, you're raising this to an even power, okay, which makes it positive. Okay, then you're taking the cube root. So because you're raising it to an even power, you're getting the same answer for both. Okay, so I've got negative, negative. Let's look at concavity. Okay, it's concave down in both of those intervals. Okay, but I have a critical point at the origin. Okay, a critical point at the origin. It decreases down to my critical point, and it increases away from it. So what could that graph possibly look like? Okay, so here's my graph. Here's my origin. The function is decreasing and concave down to the left of the origin. So decreasing means it has to slope from top left to bottom right, and concave down means it would look like that. Okay, everybody all right with that being decreasing and concave down? To the right of the origin, it's still concave down, but according to my first derivative, it's increasing. So increasing and concave down. Right? So this is decreasing and concave down. This is increasing, concave down. Okay, so what I have is a graph with a cusp. Okay, so see how I used f prime and F double prime to build the graph. Okay, and again, it's important to know what concave down means if you're drawing and what concave up means. Okay, and again, you're always welcome. Graph the function with Desmos and check. Okay, graph the function with Desmos and check. Anybody have questions about this one? I deliberately showed you one that was weird because, again, not everything's a polynomial. Okay, anybody questions? Okay, if you could just give me a shout out, yes or no. I just want to do one more thing with you and we'll be done. Okay, so what's the point of this example? What should you take away? Well, it behaves the same way as the other examples as far as increasing, decreasing, and concavity. But what this example shows you is pay attention to where either derivative is undefined. Okay, something weird might be happening there, like a cusp. Okay, so pay attention to the undefined spots in the derivatives. All right, here's the last one. Okay, there's a nice little summary box here that tells you what the derivatives tell you. Okay, again, increasing the signs of the derivatives tell you things. Okay, so again, if you've got a positive first derivative, okay, you're an increasing function. If it's concave up, it's increasing. Negative first derivative, right? Decreasing function, okay, and concave down. And this is the sign on the second derivative. Okay. So let's take a look at a matching exercise. These are always fun. Okay. Let's see if you can do this one. Okay. You try example 6. Okay. Type your answers in the chat. Okay. So now, just so you understand, here are the functions A, B, and C. Here are the derivatives P, Q, and R. So you're going to type in pairs, right? Like A, P, B, Q, okay? But they're not in order, okay? So you give this a try. We'll take a couple of minutes to see if we can do this. Start with the turnaround points, if there are any. Okay, look for those as zeros in the derivative. Okay, we'll wait for some more of you to put answers up. Don't be shy. Take another minute on this one. It turns out with this example, all you have to do is count the number of maxes and mins in the function, okay? Okay, folks, I know not everybody's finished, and that's fine, but let's just come together so we're all on the same page with this one, okay? I'm going to start with graph A here. If I look at graph A, how many extrema do I see? How many turnaround points? Maxes, mins? Well, I see one here and one here. What does that tell you about the derivative? It tells you, well, since this is where the graph's going to have a zero derivative, a horizontal tangent line, then the derivative of A has to cross my x-axis twice. Okay, only one of these graphs crosses the x-axis twice. Okay, so again, turnaround points of your graph are x-intercepts of your derivative. Okay, so I would put A and Q together. Okay, now let's take a look at the next graph. If I look at the next graph, how many turnaround points or extrema does it have? Well, it just has one. Okay, so this is the only place where it has a zero derivative, a horizontal tangent. So I'm looking for a graph that has one x-intercept, and that would be graph P. Okay, another trick would be this looks quadratic, this looks linear. It's 1 degree less. Okay, so EP. Notice I'm not even worrying about increasing, decreasing, okay? If they had given me more graphs that had, say, 2 turnaround points or 1 turnaround point, then I'd have to start paying attention to, oh, hey, this graph's decreasing down to where the derivative 0, increasing up to it. That means decreasing will be a negative value of my derivative. See, it's beneath the x-axis. And increasing means positive value. See, it's above the x-axis. So this graph also matches on increasing, decreasing. Right? Now, again, by process of elimination, we'd say C would be R because it's the only one left. Let's take a look. This does not have any turnaround points. So its derivative should not have any x-intercepts. Okay, another giveaway would be this looks exponential, and you might remember the derivative of an exponential is also an exponential. Okay? Does everybody understand the reasoning behind it? Everybody understand the reasoning? Anybody have questions about this example? Okay. Just going to wait a minute, see if anybody has a question. Okay. Coming back to the meeting and ask again questions on any of this. Anybody have questions on any of this?